Now, extend my apology for the delay of half an hour. It was due to the technical error. Now, let us begin our keynote talk number 1. Dr. Leonardo Israel Farhan Cabrera, I would like to welcome you, sir, and we are feeling honored to have you as a keynote speaker. Dr. Leonardo is a professor, researcher at the Escuela de Ingeniería Sciences campus, Puebla, Tecnológico de Monterrey. He is also a member of the Nanomaterial Research Group at School of Engineering and Sciences. He obtained his Doctor of Science in Mechanical Engineering from Unidad Calihuan. He has published more than 30 research papers in various international journals. He has expertise in subjects related to automotive engineering project, material applications, material technology, mechanical engineering, capstone project. His research domain include the current state and future trends of critical technology of electric vehicles producing energy consumption by friction losses. He has been awarded with the Mexican Research Certification Level 1. The topic of his talk is exploring EV's technology producing energy consumption by friction losses. This talk aims to provide an exploration and review of current and future technology producing energy losses by friction in electric vehicles. This review gives an understanding of the most critical mechanical components which require of performance improvement for allowing higher efficiency in electrical vehicles. Now over to you, sir. Please welcome Dr. Leonardo. Please unmute, sir. Please unmute, sir. Okay.
Thank you very much, Dr. Abshik. Sorry for the delay. I had some troubles with my connection to the Microsoft Teams, but now I am here. So I would start with the presentation. So I hope I can recover the lost time. So let me share my screen with my presentation, please. That's it. Can you see the slide?
We can see, sir.
Okay. So the name of my presentation is the exploring of EV's technology producing energy consumption by friction losses, and with a special focus on the current state and the future optimization trends on this kind of technology in all the world. So this exploration is based on a literature review survey, considering the most recent papers and the most recent chapters and technical notes and technical articles published around the world. So it recopilates the most outstanding information and the most outstanding developments about this kind of technology for EVs. So the first term to understand the content of this presentation is named Tribology. I don't know if maybe you can have learned or have known about this term. Tribology is a branch of the mechanical engineering focused on the study of the science and engineering of the interacting surfaces in relative motion. This concept is too general, but it applies for any engineering application in which we can study. For example, the most important to know about tribology is that any pair of materials producing friction or exhibiting wear and having a lubrication or requiring a lubricant for diminish up both friction and wear can be considered as a tribology topic of for understanding. Okay, so considering this concept about tribology, so we can define what is a tribological component. This is very important because usually we know mostly mechanical components, but we cannot classify them according to their special function. So tribological components have the special function to operate producing friction or exhibiting wear with the long term of operation. So how can I define a tribological component? This is the definition for a tribological component. It can be any mechanical element, lubricated or unlubricated, acting in relative motion in a mechanism or in a machine, producing friction and wear through its operation. So maybe these kind of mechanical elements are very useful, are very common in machines, but most of them have to be improved and have to be certain characteristics to exhibit a high performance, especially for electric vehicles. So most of these kind of components are involved in the new infrastructure of electric vehicles. So my task in this talk is to introduce or to present the most important or the most critical technology based on tribological components, which are the only components producing friction in electric vehicles. So to start the comparison, or to start the introduction for this kind of technology, I would like to start with the current technology in internal combustion engine vehicles. For example, in this picture that I am showing you, we have a lot, hundreds of mechanical components interacting together to produce the different tasks or the different functions inside the vehicle. For example, we have special components which are tribological components, and they are divided in the following: the tires and the road system, which are the most important. If we don't have tires, we have never moved the vehicle in the roads. So this is the most important tribological component. The other is, or there are different mechanical elements comprised in the engine. Another category is the tribological elements comprised in the transmission and the brakes, of course. Some elements in the suspension system, some elements in the steering, as well as in the differential system. Some miscellaneous, for example, belts, pumps, oil, water, and fuel pumps, the alternator, the compressor, etc. And we will have another kind of tribological components named accessories, which involves the wiper blades, the seat belts, air conditioning system, etc. So the most important thing here is to realize how many components are involved in internal combustion engine vehicles. So all of them produce a certain amount of friction, which produces the energy consumption of the vehicle. So the challenge for tribologists or for mechanical engineers is to reduce as much as possible the friction caused by the operation of most of these components, with the exception of some components required to exhibit high friction levels. For example, we cannot reduce friction in tires, of course, because if we reduce friction, we will lose traction from the vehicle to the road, so we will never move the vehicle. The tires will tend to slip, and it is obvious, right? So another part or component that will not lose or will not will require high friction levels are the brakes, for example. If we have low friction in brakes, maybe we cannot stop the car quickly, or maybe there will be vibrations or noises due to the not control of friction. So there are many components producing friction energy consumption by friction losses in internal combustion engines, and these losses can be distributed in the following way. For example, if we consider the 100% of full energy supply to a vehicle, we will have different energy losses, right? For example, the most common or the most known losses in an engine or an internal combustion engine is the losses caused by the exhaust gases or the emissions in the engine. Another is the cooling of the engine, and only the 38% of the total energy supply to a vehicle, to a internal combustion engine vehicle, will be dissipated or will be used to provide the mechanical power to the vehicle. So these are the most important losses, but they are related to heat losses. So in order to find the friction losses, we need to study more about the mechanical power. For example, in this case, we have two types of losses in the mechanical power. The first one is the friction losses, which comprises the 33% of losses from this 38%, and the another one is the losses by air drag, which is ascribed to the aerodynamics of the vehicle, but the most important here is the high levels of friction losses during the mechanical power transferring or supplying. So from this amount of friction losses, we can divide these friction losses in the following. We will have 4 different sources causing friction losses. The most important is the engine, which causes the 11.5% from the total energy supply, and we will have 5% of losses in the transmission system. What is the transmission system? The gearbox, or maybe the CVT transmission, or any kind of transmission, but it is around the 5%. So another important thing here is that in friction losses, it is considered the rolling resistance. The rolling resistance of the vehicle is the resistance produced by the motion of the wheels against the pavement or against the floor. Okay, so this is not considered as a loss, but it is into the friction losses. But actually, it is not considered as a loss. Okay, so the another thing, or the another component or system producing friction losses are the brakes. The brakes, as you know, produces a transformation from kinematic energy to friction just to stop the car. Okay, especially in internal combustion engine vehicles. So what is the concluding remark in this part? That it is that from the total energy supply, to the vehicle that can be diesel or can be gasoline or biofuel, any biofuel. Only the 21.5%, this part of it, are used to move the car, right? The rest is ascribed or is considered as a loss of energy. So this is because the internal combustion engine vehicles are not considered as a good option to get an environmental eco-friendly demands in the world. So we need to face these challenges to reduce as much as possible these losses, especially in engine and transmission. This is the labor of tribologists. So in the case of electric vehicles, we will have different distribution of energy losses. For example, the first thing to consider is the energy supply. In the case of internal combustion engine vehicles, we will use fossil fuels or maybe some biofuels, right? But in the case of electric vehicles, the main source of energy will be the electricity produced by a grid. Okay, this electricity will be produced, or it is produced from different sources, ecological sources, or maybe from a thermoelectric plants. I don't know. It depends on the infrastructure of each country. So when we supply the energy to an electric vehicle, which is based on or which is powered by a battery, this distribution of energy is based on a battery electric vehicle. So the total energy supplied to a battery will be divided or will be spent in different ways. The first one is that we will have some losses in the charging and discharging of the electricity from the grid to the battery and vice versa. Okay, so the other point here is that we have a 6% of something called energy recovered. I will talk more later about this recovered energy, but we will have ready to use 96% of energy supplied from the grid. Okay, for using in our electric vehicle. So from this energy, we will have some losses, which will be spent or will be dissipated in the cabin heating and ventilation, the power electronic losses, and the electric motor losses. These losses involves different ways of losses. For example, heat, maybe vibrations, maybe electric losses according to the efficiency of the systems of the electronic and electric systems in these 3 points, and the other kind of losses will be in the sector of mechanical power. Okay, so from the point here is that from this 96% of the total energy ready to use in the electric vehicle, the 80% will be used for moving the car, okay? In contrast to the internal combustion engine vehicles. So from this 80% of mechanical power, the 57% of this energy will be dissipated in friction losses. These friction losses will be, these friction losses are spent in different systems in the electric vehicles. The first one and the most important is again the rolling resistance. This rolling resistance is unavoidable in any vehicle, right? So the largest part or the largest consumption of energy in electric vehicles will be by the contact of tires with the pavement. So it is not serious as in internal combustion engines, but it is also considerable. So we will have again friction losses in the electric motor and friction losses in the transmission when we have powertrains, when the electric motors are coupled to fixed gears or gearbox. So in this case, we will have around 4% from the total energy supplied to the battery dissipated in friction losses in these two parts. Okay, the another parts are not considered as friction losses; they are considered as losses required for moving the car. And the other is the brakes. The recovered energy supplied to the battery, the extra energy supplied to the battery, are produced from the kinematic energy recovery system, which is provided by the double purpose or double function of the electric motors in electric vehicles, which can be used as an electric motor, or they can be used as a generator of electricity when the vehicle is stopping, right? So this recovering is very important in electric vehicles. So what is the challenge to face, or what is the most important thing to consider in technology used in electric vehicles? Well, we need to improve, or we need to enhance the performance in terms of friction of electric motors, transmission systems, and all the electronics and mechanical components involved in these three parts: cabin heating, ventilation, power electronic, and electric motor, and other miscellaneous, as similar than internal combustion engines. So what are the main components, or what is the technology producing the friction losses? There are many components that we will see in the another slide, but previous to this slide, I would like to ask this question: why consider Tribology as an automotive improvement key route, especially for electric vehicles? Well, Tribology offers a reduction of fuel and energy consumption in general. Even the smallest reduction in friction could represent a significant energy save in an electric vehicle. So considering that electric vehicles tend to be autonomous in a near future, or maybe a short-term future, the autonomy of the vehicle will be led by the durability of the battery in terms of energy, right? So if we can reduce the consumption of energy by reducing this the friction generated, we can improve the duration of the battery for getting more distances run by the vehicles. So this is the most important thing. The another is that if we reduce the friction, we can improve, or we can increase the engine power output. So we can take more advantage of the electric motor, or the power of the vehicle. Another is the improvement of durability of all the components exhibiting wear in its operation, and the reduction of vehicle maintenance in general, right? And finally, in electric vehicles, it is very important to consider that we need to reduce extremely the vibrations and noises, because considering that we won't have any more internal combustion engines, causing high levels of vibration and high levels of friction by the exhaust. In electric vehicles, they are very there are no noises when they are operating. The only noises occurring in electric vehicles are the noises produced by the electric current through the entire vehicle, and all the noises produced by some misfunctions for another components. So the reduction of friction or the control of friction could help us to provide or to maintain low levels of noises and vibrations in our electric vehicles. So in the case of the technology, producing these kind of friction levels or critical friction levels are divided or can be divided in different parts or different categories. The first one is the main source of power to the vehicle, that it is the electric motor. The another is the transmission. Usually, it is very common finding powertrains of electric vehicles comprising electric motor attached to a transmission. It is because the transmission system or the gearbox helps to reduce the speed of the electric motor, but it improves the torque required in the electric vehicle. So it is always it is the most often architecture found in electric vehicles. So another thing producing friction are the wheel bearings. These are unavoidable elements in any vehicle as well. So the friction produced there is very critical in the vehicle. Another is all the mechanical components involved in the steering system, the tires, obviously, and the ball bearings, which are named constant velocity joints. These joints are also unavoidable because they allow us to use suspension system. Mechanically, they are also very important components, but they produce high levels of friction. Also, we will have different components in the suspension system, as well as similar than in internal combustion engines. They provide us with a comfortable driving for everyone, right? For the passengers. So another important, but they are sometimes discarded because they are miscellaneous or they are extra components in electric vehicles, are the comfort and safety devices. These comfort and safety devices are usually activated or used by consuming electricity from the vehicle. So if we can reduce the friction losses occurring in those kind of components, the energy from the battery could be enhanced, could be saved. So another are the gears or flywheel. This technology is not very common, but it is a trend of technology for saving more energy from the stopping stage of the vehicles, more than using only the electric motor as the twofold purpose of regenerating energy. We can use as an extra the gears or a flywheel to recover this energy. And finally, we will have many, I don't remember the number, but we have around 20 or 50 MEMS or NEMS used for sensing the different operation of the vehicle. So these are the most critical technology, and I will talk about each of this category. Starting with the electric motor, we have different electric motors considered for which can be considered for electric vehicles. The most important is the synchronous permanent magnet motor. Actually, it is the most used in sport cars or in passenger cars, and the other four are also an option, but they are not so popular than the synchronous permanent magnet motor. So they are rated according to their efficiency in terms of electric efficiency, and as you can see, the most efficient is the brushless, right? The synchronous brushless motor. So, what is the constant or the similar or the constant mechanical element or tribological element producing friction losses in all these type of electric motors? The main is the rolling bearings, or bearings. Okay, this is the most common element producing friction losses, and in the case of brushed motors, we will have this element that is one of the causes that this motor is not suitable for electric vehicles. It is because the brushes and slip ring contact produces high levels of friction and electro friction due to the sliding contact produced in this component. So the efficiency of this motor is lower than this one, because this one doesn't use a brush and slip ring contact. Okay, so what is the trend to improve or to reduce the friction produced in these elements, in particular the rolling bearings? Well, we need to work, or we need to conduct research on grease technology, different coatings for the balls or the rollers in the bearings, and new design in rolling bearings. If we can improve some of these points, or even the 3 points, we can reduce in significant amounts the friction produced in these kind of motors, right? In the case of brushes and slip ring, there are some words attempting to reduce the friction produced by the electro tribo contact, and there are some pair of materials meeting with this purpose: the graphite and graphite, coin silver, brass fiber. But there is a very huge challenge in tribology for this component. That is the getting of a better understanding of the electric tribo contact produced in this brushes slip ring contact, right? So in the case of grease technology, we will need to understand what is the composition of a common grease. A common grease is bearing grease is made of mainly of 70 to 95% of a base oil, which is commonly made by using mineral or synthetic oils. The 3 to the 30% of the grease is made by a thickener. This thickener can be made of simple metal soaps or complex metal soaps, or maybe some non-soap thickeners, and the rest is made of additives, different kind of additives. Each additive produces certain physicochemical property to the grease. It is very important. If we can use as a constant these 2 points, but the addition of additives will define the specific properties that the grease will have. So we have different or an evolution of the production of greases for electric motors or for rolling bearings. The first grease used by humanity are the animal fats. This is very known for everyone. The animal fats were used by Egyptians and Romans. This is the first report of the using of a grease for helping to transport heavy loads. And then with time, different compositions of different greases have been produced. Currently, the research on this lubricant is based on the using of carbon nanotubes, some kind of nanoparticles, discarding the use of mineral oils or fossil oils by using bio oils or bio greases, and using some thickeners or some high performance thickeners through the implementation of advanced polymers. So this is our trend, and in electric motors we can implement some enhanced or high performance greases developing in these days. So the current progresses are the developing it is the developing of producing greases made of synthetic oils, vegetable oils to meet with the new eco-friendly demands in the world by using thickeners made of rubber, polypropylene, and methyl pentane, and using a wide range of new additives produced in the world. So in the specific case of electric motors, there is a challenge, a current challenge, that is specifically based on the improvement of a property called tackiness. Tackiness is a grease property that allows the sticking and formation of long threads between two separating surfaces, mainly in gears or mainly in the rollers and in the bearing, in the rolling bearings. Well, the grease redistributes itself between the surfaces. So this property can be said that it is the most important requirement for greases used in EVs or in electric vehicles. So finally, we cannot discard the use of bio oils or bio greases for producing electric vehicles greases. Okay, so in the case of transmission, we will find this common configuration and these common architectures. The first one is one of the most popular is the in-wheel motor system, in which electric motors are attached directly to the front wheels, and these wheels are moved independently by each electric motor. So this is the most efficient because there are not a gear transmission, or there is not a gearbox attached to the electric motors, but this system has some deficiencies. For example, they have a low and limited top speed because we have directly the connection of the electric motor to the wheels, and excessive tire wear and overuse produced due to tire slip. As you can see, the electric motors are attached to the front wheels, but when the electric vehicle is going to take a curve or to turn to the left or to the right, each electric motor should or must control the speed independently for each wheel. So in this process, the tire is produces a slippage with the road. So the wear caused to the tire is very high. So this is the most important deficiency. What are the improvement trends? The first one is the using efficient electric motors in this configuration. Improve the control of the electric motors in this kind of configuration. Producing an efficient grease and using rolling bearings with very low friction. The second kind of architecture is an electric motor attached to a fixed gear, and this fixed gear is attached to a differential in the front wheels. It can be also to the rear axle, but in this kind of configuration, it can be used also in the front axle. So what is the problem here? The problem here is that we have a fixed gear or a gearbox that produces high levels of friction. So this is the main problem because there are more moving parts. But this configuration helps us to increase the vehicle driving range and top speed, having a satisfied dynamic performance and easier speed control, right? And finally, we have a central motor with a multi-speed transmission. This configuration is not so popular. Actually, it is a current research trend for electric vehicles, using an electric motor attached to a clutch or to a wet clutch, and this clutch is attached to a gearbox. This is because this gearbox can be used according to two different speeds, or we can use a multi-speed transmission, for example, a CVT or a automatic transmission. I don't know. The point here is that we need to have a gearbox that can be switched for two speeds. And the problem here is that we have many more moving parts because this gearbox will have many more gears and many more synchronizers or another element inside. But it exhibits some significant advantages. For example, more improved overall efficiency for the powertrain, more increased vehicle driving range and top speed, and it enables the electric motor to operate in higher efficiency regions, reducing energy consumption. As I mentioned before, this configuration is still in research for different companies. So, but it can be important to consider for future investigations or future developments. So, what is the improvement trends? In the case of gears, in these two configurations, we can modify the gears inside the gearbox by using low friction coatings or some kind of texturing in the gears. In the case of dynamic seals, because all these elements will have dynamic seals, is by using low friction materials as well, surface texturing, and improved polymer lubricating oil compatibility. This is more like wear problem, right? Caused by the lubricant incompatibility with the polymers either in the electric motor or in the fixed or in the gearbox. And finally, choosing the appropriate lubricating oil is really a challenge in this technology. Lubricating oils are expected to change in the coming years, especially for electric vehicles propulsed by electric motors attached to fixed to certain transmission, right? Because the electric motors are inside the transmission system or the gearbox, and the whole system is lubricated by using the same oil. So there are some problems. For example, the electrification of the shaft, the entire shaft, can cause some bearing currents, or can cause some gear currents or leakage currents from the electric motor to the shaft, producing premature wear in all the mechanical elements that you can see inside the powertrain. So these lubricating oils must meet with new standards or new demands for specifically these kind of powertrains. For example, the resistance to corrosion should be improved, especially for Cooper elements, because we will have the lubrication of the entire wire of the electric motor, and also we will have different alloys and metals in the entire powertrain. So if the lubricating oil is not resistant to corrosion, or it not isolate the corrosion in the system, all the elements there will be corroded and will fail in very short time. So the other thing is to improve the compatibility with polymers, especially with resins used in the wires of the electric motor. Most of lubricating oils existing today are, especially for gearboxes, have some acidic components in its composition, so they can damage the polymers. For example, resins or certain O-rings or certain seals used in the powertrain. So if the lubricating oil does not meet with this compatibility, any electrical device will fail just by the contact with the oil. So another controversial topic is, what about the dielectric properties of the oil? As I mentioned, it is expected to have bearing currents or leakage currents from the electric motor to the shaft. So it is not known if the best is having a dielectric oil or having a non-dielectric oil. It is not specified by manufacturers already, but the most accepted theory is by using lubricating oils with high levels of insulating, of electricity insulating. So considering that these new demands in lubricants have not standards or current standards for being applied or for being used in powertrains, we need to develop new standard methods for testing these kind of lubricants, especially for controlling these problems, right? The problems of bearing currents, the problems with compatibility with polymers or resins involved in the electric motors, and the problems of corrosion, especially for Cooper. So this is a challenge currently in the community of engineers, electrical and mechanical engineers, and another trend is the using of more improved synthetic based oils. This is the challenge, because these synthetic based oils are very often used in high demanding applications, but they have not been tested for being used in electric powertrains. So another is not discard the eco-friendly demands. So we can blend or we can formulate new electric vehicles lubricants by using certain amounts of vegetable oils. It is well known that vegetable oils exhibit better lubricity than even synthetic acid oils, but the problem with this kind of oils is the low resistance to oxidation. So the durability of this kind of oils or this kind of lubricants based on vegetable oils is the durability. So, but we can improve the durability or we can improve the resistance to oxidation by adding certain additives. So the formulation by considering either synthetic oils and eco-friendly oils is also a challenge, right? Well, in the case of a steering system, we have certain or this system that is quite useful if we consider that the electric vehicles will be autonomous in a near future, right? This steering system is named Electric Power Assisted Steering System, and it consists on a conventional mechanical system for driving, but there is a servo unit attached to the torsion bar just to produce the movement of the wheels, right? By assisting the steering of the wheel of the car. So we have three different configuration of this EPAS and we will have different mechanical elements producing friction. So as I mentioned before, between the largest amount of mechanical elements or tribological elements producing friction will be the largest consumption of energy in the electric vehicle. So the challenge here is to use the less number of mechanical elements as possible. So in this case, we have an steering column that have a steering wheel, the torsion bar, and universal joints producing friction losses. We also have the servo unit, which comprises the electric motor, the torque sensor, and the pinion and rack or worm gear that is in charge of producing the movement of the wheels mechanically. So, and finally, we will have the tie rods that are the pieces used to connect the rack and pinion gear with the wheels. Okay, so these three systems are high consumers of energy from the battery. So we have some technological improvements to reduce or to eliminate these mechanical elements, and the most attractive is again the in-wheel motor system. In this system, we totally discard any of these components by only using a motor by controlling the speed for turning to the right or turning to the left. And the another system is the steer-by-wire system, in which all the torsional or the steering column is eliminated, and only we have pinion and rack gear acted by an electric motor, and that's it. Okay, the motion of this pinion and rack to move the wheels is produced by a signal sent by a computer in the wheel. It is not totally sure or totally confident for the user, because we always need to feel the mechanical contact with the wheels just to provide security to the user. But if we don't have this contact, it will be not sure, okay, for the user. Actually, there are not currently there are some rules which avoids the use of this system because it has not improved as required for exhibiting wide levels of security. And the other component are the tires. We have different ways to reduce the friction in tires. The most common method and the most cheap or the cheapest method is by increasing the air pressure of the wheels and having a constant monitoring of this pressure. But usually this technique produces the tire slippage. It decreases in time of acceleration, it decreases in braking time, and it produces an increased wear of the tire. So we have another options. The first one is the new tire design. This is in order to reduce the friction consumption by the wheel and to reduce weight of the wheel, right? Also, if we can reduce the weight of the entire vehicle, we can reduce also the consumption. So these new trends in tire design are having more attention, especially for electric vehicles. The other one is the use of new materials for the rubber of the tire, but although they have exhibited very significant results in terms of friction and weight, the production of these new materials have certain drawbacks for a commercialization. The first one is the high cost. Another is the unreliable production techniques and uncertainty over environment, health, and safety risks, right? Because there are some materials, dangerous materials for humans. And the other one is to control the operating parameters. For example, controlling again the pressure or the air pressure of the tire, the driving speed, and the tire air composition. We can use a different gas inside the tire, different from conventional air or environmental air, right? So then in the case of wheel bearings, we have two different types of wheel bearings. It depends on the manufacturer sede. The first one is, or we will have vehicles having this kind of wheel bearings, and we will have vehicles having these kind of wheel bearings. Actually, it depends on the production country of the vehicles. For example, in United States, the vehicles produced there are produced by using these wheel bearings, and in Japan and European countries, they use these kind of bearings. Okay, so what is the common, or what are the common components of these bearings causing friction? One is the polymer seal that avoids the leakage of or the spreading out of the grease. The another is the grease, obviously, and the final is the rolling bearings used in the bearing. Okay, so what are the improvement and development trends? One is the new designs by reducing weight, by improving the maintenance periods, improving the sealing capacity of the seal, and improving the grease. Okay, so with new design, we can reduce the size of the bearing, and if we reduce the size of the rollers, we can reduce friction and we can reduce weight. Also, we can use some interesting coatings which are currently developed. The most important or the most remarkable is the DLC coating, that is diamond-like carbon coating. It is the coating exhibiting the lowest friction levels in any kind of application. So in the case of grease technology, we need to take into consideration the developments presented in the previous slide, And in the case of constant velocity joints, maybe we cannot imagine what is a constant velocity joints, because it is a very important mechanical component, right? So this is a mechanical constant velocity joints. This component in here is the constant velocity joint, and it operates by using a kind of roller bearing. It uses a grease and it uses a boot. The boot is a seal in order to avoid that the grease spreads out from the bearing. Okay, what is the problem here? The main problem of this component is the rupture or the failure of the boot. With time, we will never realize that our boot or the boot of the constant velocity joints have been failed. So the problem here is that the grease spreads out from the bearing, and with the long-term use, the bearing is failed. So it causes a lot of friction losses. So it is a critical component even in internal combustion engines, but also this component will be used also in electric vehicles. So we need to take care about the performance of this component. So the most important thing to consider for the improvement of this is the grease technology, but the compatibility with the rolling bearings and the compatibility with the boot. If we improve these 3 points, we can improve the performance of this component. Another technology important for and that is a current trend in research is the kinematic energy recovery system, especially the flywheels. This is a technology used to recover as much as possible the energy dissipated by stopping the car when it is running, right? Everyone knows that the electric motor used in electric vehicles can be used also as a generator. So when we use the electric motor as a generator of electricity, we can recover electricity, but it is not totally efficiently. So we need to use a mechanical technology that help us to recover more energy from the stopping step. So this is a flywheel serving as a gears for energy storage. The main purpose of this is to connect the wheels during the stopping to a certain mechanical arrangement, and to get this mass or this flywheel to rotate at high speed, right? The inertial mass and the speed is energy storage, and when we want to use again, we only need to connect this moving flywheel again to the wheels, and the wheels will rotate with more power. So this is the main the basics of the function of this component. So the advantages are the high power and energy density, the availability of output energy directly in mechanical form. It means that we don't need to transform electricity to kinematic energy to electricity, and the electricity being storage to the battery, and the battery again to the electric motor and produce the power. In this case, we have always mechanical energy that can be connected directly to the wheels, and it is easily absorbed. Okay, and also the another advantage is the high efficiency. However, there are Actually, there are two different kind of typical configurations. The one is using an slipping clutch to connect this flywheel to the wheels, and the other one is using a brake assisted by the electric motor or by the disc and pads in the braking system. Which are the deficiencies? The first one is the torque transmission losses in the clutch and brake system. We have friction in this part, so some part of the energy recovered will be dissipated in friction and heat, and also friction losses in the flywheel bearings. The flywheel will be rotating through the use of a bearing or of a pair of bearings. So the friction produced in the bearings will be significant in this technology. So there are current trends in the improvement of these systems. One is the understanding and the development of new superlubricity effects in rolling bearings and the superconducting magnetic bearings for these systems. So these are very, very novel problems or novel or complex technologies or complex sciences, but in a future it can be implemented in these kind of systems for improving the electric vehicles. So in the case of comfort and safety devices, we have an unavoidable system that provides us with comfort, especially in countries where there is an extreme weather. This is the air conditioning system. This perhaps can be considered as an unimportant component producing friction losses. However, it is one of the main sources of energy consumption in an electric vehicle. Use it, for example, in winter, or use it, for example, in summer when the weather is extreme. So there are some different configuration of these mechanical systems, but there are some improvement trends. The most improvement trends for reducing the friction caused in these components are the using of sliding elements made of different materials, causing very low friction. For example, polymers, or again DLC, or diamond-like carbon. Okay. The another one is the using of refrigerants with exhibiting low friction coefficients during the process of the air conditioning. For example, the most important is the using of CO2 or carbon dioxide. This is for two things. The first one is that it exhibits the lower friction coefficients in the system, and the other one is the eco-friendly demands or the lowest damage caused to the environment by using this refrigerant. However, it is not a rule. Actually, it is not accepted in any country to be used as a refrigerant, but the trend is to investigate more about this. In the case of lubricants, the main lubricants used are the synthetic polyester and polyalkylene glycol. These lubricants are used together with the refrigerants inside the air conditioning system, and they are lubricated together with both fluids. As a note, I can say that if we reduce the friction in this source or in this component, we can reduce the the energy consumption in battery of electric vehicles. So it can be a very critical mechanical element considered for the improvement of electric vehicles. So in the case of suspension, I will focus in shock absorbers. This is because in electric vehicles, it will become a really problem, in particular when in terms of comfort of the vehicle. We have different kind of shock absorbers, and they can be active, passive, or semi-active, and they can have architectures like twin tube or monotube, but this is the most common in vehicles, right? So what is the purpose of this shock absorber? Well, this stud in this part can be moved up or down when the vehicle is moved, or when the tires are moved, are rolling, and there is an oil seal. All these parts are lubricated by using an oil, but when this stud is moved in this way, there is a friction produced in this part. This seal avoids the leakage of the lubricant contained in this part to the exterior. So the seal is a dynamic seal that promotes the movement of this bar, but it avoids the leakage of the fluid. Okay, so when this polymer, when this component is wear off, it produces noises, right? This is the most important point to consider for electric vehicles, the noises, because in internal combustion engines, we are very used to listen or to hear the noises from the engine in the vehicle. The most important is the engine noise and the exhaust gases that produces noises, right? But in electric vehicles, we eliminate those noises, right? We will use an electric motor that it is very, very quiet, and we don't have it doesn't have exhaust emissions noises, right? So the only noises that we will hear inside the electric vehicle will be the current flow in the electric vehicle, the electric motor, but it is very, very quiet, and that's it, right? So there will be some noises more palpable when we are driving, and these noises will be only produced by the misfunction of different systems. For example, the wear in the wheel bearings, wear in the shock absorbers, and wear or misfunction in the brakes, right? So in the shock absorbers, the squeak noises are very, very uncomfortable for the passengers. So this is the thing to improve in this kind of components. So we can use novel or advanced oil fluids. We need to use or to develop new hardware configuration for these kind of components, and advanced seal design and materials, right? So finally, the electric vehicles have different microelectromechanical systems, also named as MEMS or NEMS in the case of the Nano. These systems are involved in the sensors in electric vehicles. For example, we will have inertial MEMS. There are some examples of the sensors which are based on inertial MEMS, the pressure flow MEMS, the infrared optic MEMS, and the radio frequency MEMS. So in this case, we have a hybrid hybrid vehicle, but most of these MEMS are used in electric vehicles. Now, if we consider the use of other technology to become our electric vehicles to autonomous, we will use more and more micro electromechanical systems. So the problems with these microsystems are the high levels of extinction because of the size of these sensors, the high dynamic friction, also due to the low or due to the size of the sensors and wear. Right, when some of these point fails in the sensor, it is a total fail in the sensor. So the adhesion is the main problem, but there are some research trends to reduce the problems in this kind of sensors. The first one is by using self-assembled molecular coatings, treating a hermetic packaging, producing a surface modification on the sliding parts in the sensor, and using dry lubricants in the sliding components. So this is all my presentation. I think I take more time that I was accepted. I want to invite you, if you want to know more about this kind of tribological components in electric vehicles and the trends, you can get access. Actually, the paper is an open access source. You can read if you have more questions, or you can read more about it. Thank you for the time. Thank you for the invitation for this presentation. Gracias.
Gracias. Thank you, Dr. Leonardo, for your informative talk. It was very informative research talk, and naturally, most of the participants felt in that way. Yes, they got something very informative. Sir, we have a question that is from Paramjit. Hello. Yes, we have a question from Paramjit Singh Jamwal. He is asking how we are considering 7% motor losses.
How can we consider the 7%?
Yes, 7% motor losses.
Okay. Are you referring to this 7% motor losses, right?
Yes.
Yeah, it comprises the motor friction losses, the bearing losses, or the roller bearing losses, plus the electric losses and heat.
Okay.
In the electric model.
I think he got his answer, and there is no more questions, sir. And yes, there is no question, sir. I would like to, naturally, there is a request from Dr. Dubey. He's a convener. He please accept his sincere gratitude for all your cooperation we have been receiving. And naturally, it was very informative talk. Let us now conclude your talk, sir. Please, while you leaving, please press leave. Do not press end button. Okay, sir. Okay, when you leave, sir, please press the leave button. Do not press the end button. Okay.
Okay.
Because it is in continuation. Because we have next speaker on the same row. That is the reason. Okay, sir.
Okay.
Okay. So thank you very much.
Thank you very much.
Okay, sir. So now let us invite our next speaker.
Ashish, sir, actually,
yes.
Next speaker is in process of joining. We can wait for 5 minutes.
Okay.
Yeah.
Okay. So he's in the process of joining. It will take 5 minutes. So we are waiting for it. So let us wait for 5 minutes for the next keynote talk. Thank you. Moving to pre-live. Can we move to pre-live right now? We can take 5 minutes.
Ashish sir, we just hold for the presentation. Okay. I think so. Sir can leave.
Sir can leave, please.
Yeah. Thank you very much, sir.
सर मैथ्यू डायसन जो है ना सर ये कनेक्ट नहीं हो पा रहे हैं अभी।
Vishnu sir, Abhishek sir, you can unmute yourself. I think so you are muted.
Yes, we are in the process of joining. Please, we have to wait. Naturally, key talk number 2. It was naturally scheduled for Dr. Gunti, and due to some certain emergency, his talk has been rescheduled, and the timing or the rescheduled will be informed later on. So we are moving to the key talk number 3 of Dr. Mathew Dyson, and we are waiting. He's joining in a short while from now. Sir, welcome. Hello.
Yes, sir. Yeah,
Can you hear?
sir, Ashish sir, you can start.
Okay. Sir, please unmute your mic. Dr. Mathew, please unmute your mic. Dr. Mathew, please unmute your mic.
There we go. Is that okay? Can you see this? Yeah.
Yes, sir. Welcome. This is Dr. Abhishek, the Master of Ceremony. Let me introduce Dr. Matt Tyson, the keynote speaker. Dr. Tyson, we welcome you in the FlexEV 2021. Dr. Tyson is a technology analyst at IDTechEx, specializing in printed, organic, flexible, and hybrid electronics. Mathew has previously been involved in research across a wide range of printed, flexible electronic areas, contributing to 15 scientific papers and presenting his work in a variety of international conferences. At IDTechEx, he analyzes companies and technologies in the printed, flexible sector, accessing innovations from a technical and commercial perspective. Today's topic of his talk is opportunities for printed flexible electronics in automotive applications. The automotive sector is experiencing a period of a rapid change with a transition to the electric and autonomous vehicles. This creates an extensive range of opportunities for printed flexible electronics within the powertrain, interiors, and even exterior. For electric vehicles, the main opportunities are in battery monitoring with thin films that can detect pressure and temperature. This is the formal introduction of his talk. Now I request Dr. Mathew to begin his talk. Please, Dr. Mathew.
Thank you very much. So first of all, I'd like to thank the organisers for inviting me to this event, and also to apologise for these technical difficulties. I could see the talk, but for some reason not kind of getting to presenter mode and share my screen. So I'd like to talk today about the opportunities for printed and flexible electronics in automotive applications. And so that doesn't just cover electric vehicles, but covers all types of cars. And some of those sort of transitions, such as an increased focus on the interior, are a function of the transition to electric powertrains. So just before I start, I'd just like to introduce you to IDTechEx. So we're a company that provides technical market research, and we aim to both sort of track and predict the future of a wide range of emerging technologies. You can see some examples there. So that includes identifying new technologies, estimating market sizes and market forecasts, looking at different companies, that kind of thing. So if you're interested in any of that, please get in touch. So here's the outline for my talk. I'm going to start briefly by outlining, how we perceive printed and flexible electronics, then move to the motivation for using such technologies in automotive applications, and then look in more detail, and this will be the bulk of the talk, at these three different application areas: the powertrain, the interior, and the exterior. And you can see from all these bullet points, there's a wide range of opportunities within vehicles for printed and flexible electronics. So just to sort of briefly start, so we're all on the same page, if we think about printed and flexible organic electronics and how it compares with traditional approaches, there's quite a lot of differences, aside from the obvious flexibility. So you're looking at having manufacturing methods that can be achieved at low temperature. Obviously, that has kind of environmental benefits, but it can also speed up the actual rate of processing, leading to cheaper manufacturing. But as it's printed, all or most in the case of hybrid, of the functionality can be processed from solution. And so, with printing with conductive inks, that kind of thing. You can be applying these to all kinds of substrates: plastic, textiles, paper. In a car, it's primarily going to be onto plastic, but in other applications, not necessarily. And of course, it's an additive method, so we use less material, which can be a cost saving and obviously an environmental benefit as well. And so There's an awful lot of different technologies and materials within the kind of umbrella of printed flexible organic electronics. You can see some of these here. And I'm obviously not going to go through all of them, but the basic idea, as with most manufacturing, is that we take some kind of material, and in many cases those are quite innovative in themselves, to create some of these different technologies. So, for example, photovoltaics and sensors and displays, all of which I'm going to be talking about in the context of vehicles later on. And they can end up in lots of different industries because of the benefits that we can see over on the right. And in reference to the cars, the lightweight is really important, the thin form factor, and even the transparency can all be useful. So if we look at all of these features a little bit more detail, you can see a whole range of benefits here. And as I say, the lightweight is one that's often missed. People are very keen to talk about the flexibility and the sort of compatibility with large area manufacturing, and perhaps a little bit less keen to talk about the fact that fundamentally printed and flexible electronics are lighter because you're not having to use a sort of big rigid piece of FR4, and because it's conformal, you can kind of wrap those electronics within a smaller package, which means that there's less other material used for the housing. And particularly in a vehicle, where the range of an electric vehicle is important, or you want lightweight for handling, that reduction in weight, I think, is really important. So if we look at the kind of market drivers, again, there's a whole range of factors why people would want to transition from conventional electronics to printed electronics. And you can see, this sort of breakdown here with people looking for this conformality, large area. And in some cases, the kind of performance is better, such as in an OLED display, but often that's not the main driver. More often it's to do with these sort of form factor type properties rather than kind of absolute performance in terms of display resolution or sensitivity or in a sensor. And if we look at the kind of market, the vast majority of it is OLED displays, but there's various other sectors there. The second largest of which is sensors, and that kind of breakdown is translated pretty much into vehicles as well, where the biggest applications will be sensors, OLEDs, and possibly a little bit of changing the manufacturing methodology of a car and replacing wiring as well, such as in-mould electronics. So down at the bottom of this slide, I've got a few different ways in which you can incorporate printed and flexible electronics sort of into a product. And broadly speaking, there's three here. So you can either just replace something. So that might be replacing an LCD display with an OLED. And again, we'll see that in vehicles. You can significantly improve something. So, for example, the seaters and the heaters in car seats currently made out of wires primarily. So by printing those, you can move them further to the surface, reduce weight, improve the response time. And so that demonstrates an improvement. Or you can create a whole new product category and replace nothing, basically. So some examples in a car might be putting displays on the outside of an autonomous vehicle to signal to pedestrians, or incorporating sensors throughout the seat for monitoring passenger well-being rather than just merely detecting occupancy as at present. So if we move on to the next section of the talk, I'd like to look at the motivation for printed and flexible electronics in vehicles. And broadly speaking, we see there's three key transitions here, and the first two are pretty obvious. I'm sure we're all aware, particularly at this conference, about electric vehicles replacing internal combustion, and it seems like every few weeks another car manufacturer announces their timeline for going EV only. And I think the government regulation, certainly in the UK, says that any new car sold has to be an electric vehicle by 2030. So I think that's a trend that is certainly happening, and everyone's on board with. The increasing levels of autonomy So, this move towards self-driving cars, I think it's going to take a little bit longer than the transition to EVs, but that's sort of certainly happening as well. There's huge amounts of money going into autonomous driving. Arguably, there's some level 3 cars at the moment, with the one recently about to be released from Honda. And that will also lead to changes in the design of the car, because if you move towards level 5, you've got to think about how those cars interact with pedestrians, but you don't necessarily need to make such a driver-focused interior, because obviously the car will be doing the driving itself. And the last transition here, I think, is a particularly important one that links very well to the idea of EVs, and that's the shift in differentiation from the powertrain to the interior. And if you go back sort of 5-10 years before EVs were really a topic, the sort of more prestige models of cars tended to have bigger engines, and manufacturers would talk about the technology in those engines as a way of differentiating that product. You'd see turbo on the side of the car, or people could talk about having a V8 or having a supercharger or larger engine. And so what really made the kind of expensive cars sort of more prestigious was primarily the engine, and then they had a nicer interior as well. But it's a lot harder to differentiate on the electrical capacity and the motor than it is with a conventional engine. It's kind of less tangible. And so as a result, if you want to sell those sort of more prestigious models, more higher priced models, you need to provide some way of differentiating them from the competitors. And so that is primarily going to be within the interior. And if you look at some of the sort of premium brands recently, the interiors have kind of certainly moved up a step. With the integration of screens and the kind of general design of those becoming increasingly sophisticated. We see digital gauge clusters, for example, where you can have a map and your speedo that's all configurable. And there was a rather nice quote I read from a manufacturer of digital gauge clusters, so obviously he's slightly biased, but they said that the cockpit is where the battleground has now shifted. It's no longer what's under the hood, it's what's inside the cockpit. And I think that's a really important idea when it comes to printed and flexible electronics, that we shouldn't just be thinking about how can we get these into the EV powertrain, but what does the transition to EV mean for the design of the vehicle as a whole, and hence what other opportunities is it opening up for printed and flexible electronics? What are manufacturers now going to be focusing on? So we look at some of these motivations. One of them, as I've already mentioned, is this idea of SWaP-C. You're reducing the size, weight, power requirements and the price. And, obviously all of those things are beneficial. So, I've just outlined some of these here. And you with the size and weight, you kind of win on both the battery range and the handling. A lighter car takes less energy to accelerate, and will also handle better in the corners for a sportier experience that you can then sell to your customers. Or you can just put more batteries in and keep the same weight and increase your range. And reductions in power, particularly for the sort of air conditioning systems, as we heard from the previous speaker, are another sort of challenge, particularly with the electric vehicles where range is such a priority. There's another benefit that's kind of not necessarily related, is this move to cheaper manufacturing. And so this is facilitated by moving from sort of sheet to sheet assembly towards roll to roll assembly. And so if you can imagine making sensors on a production line that is not dissimilar from one you might use to print newspapers, your costs can become an awful lot lower. I'm going to talk about that a little bit more later on. But certainly there's a German manufacturer who's wanted to make battery sensors in this fashion. And, you can produce these in such high volumes so quickly that your costs of the machines, in terms of depreciation, become almost negligible. And instead, your cost is basically dominated by the material. There are other ways of making the manufacturing cheaper. And one of those is in-mould electronics and film insert molding. And so rather than having discrete buttons that take time to assemble and wire up, you can instead incorporate all of that functionality with capacitive touch switches, etc., into a piece of plastic, and then you just have a single part that is lighter and much cheaper to make. And we're already seeing that. If you look at some of Volkswagen's new electric vehicles, we see that they've managed to reduce costs by incorporating a lot of capacitive touch switches rather than conventional mechanical buttons. So I seem to have missed the graphic here, but of course the other motivation here is the conformality, that manufacturers want these organic shapes and curves in the interior. If you look at a car from 20, 30 years ago, it was very boxy in the 80s. Now the curves are very swoopy. You end up with much more of these kind of organic type shapes inside. And of course, your electronics and displays need to conform to those. But we don't generally need any repeated flexing. So to summarize all of that, we've got this rather nice graphic made by one of my colleagues where we show all the different applications of printed and flexible electronics within the vehicle. You can see there are quite a lot. And so they include, things as diverse as image sensors, heaters for batteries, photovoltaics, transparent antennas, all kinds of opportunities within the car. And so again, I emphasize that when you're thinking about printed and flexible electronics for electric vehicles, we don't just want to think about the powertrain, we want to think about the car as a whole and how the design of that car is going to evolve with these transitions towards EV and autonomy. So, to move on to the powertrain, which is my next section, many of you probably know that batteries work best in a very narrow operating temperature window. So you can see over from this graph here, if we look at the graph at the top in Celsius, we want to keep batteries sort of between 15 and 20 to 5 degrees. But of course, depending on your location, the temperature outside could be a lot more than that or a lot less. And that's going to be significantly detrimental to battery performance and hence to your range. And, certainly in the UK, we tend to have more of a problem with it being cold. And so people driving electric vehicles in winter, can complain that their range is an awful lot less. 30% less in some cases than you might see in summer. And that would be, not one, the battery actually is storing the energy less effectively. And also, you've got the heated seats and the interior heaters on. And so in terms of controlling the battery and maximizing range, it's really important to control this temperature. And so there's different ways to do this. Obviously, you can kind of pump some warm fluid around, but that's not especially efficient because you end up heating up all the piping, etc. And it's quite hard to target the individual cells, which may have slight differences in how they behave due to sort of manufacturing variation, etc. And so there's some examples here of these integrated sensors and heaters for battery cells. And so you can see that one of the attractions with printed electronics is that you can combine these functionalities. And so because it's all printed, you can kind of print multiple layers or sort of laminate different sheets. And that enables you to have films that can both do the heating and do the sensing. And, depending on how you've set up the electronics, you can clearly target this. So you could have a spatially resolved sensor and a spatially resolved heater. So if a particular portion of the battery was too hot or too cold, you could adjust your heating appropriately. And we've also seen people I don't think this is necessarily commercialized yet, but it's certainly being discussed, that they'd like to incorporate pressure sensing within their battery sensors. Because if you've seen a kind of very old mobile phone where the back of it's kind of been pushed off as the sort of dying lithium-ion battery has expanded, that can be a problem. And obviously it's a safety risk there because there's obviously gas building up, etc. And so by sensing the pressure from the battery cell pouches, you could spot that early, and then not use that cell anymore or direct you to for maintenance, etc. So I think this is a big opportunity for the batteries, for printed and flexible electronics within EV batteries. And I think your advantages with printed and flexible electronics are that these sensors can be quite cheap to make and they're very light, they're conformal, and ideally you could incorporate them within the cell pouch manufacturing process. There's also another aspect here, which is thermal management in electric vehicles. And whether you describe this as electronics is kind of a bit of a moot point, but I thought I'd mention it here that as we move towards having more and more electronics inside the vehicle, both the power electronics that you'd associate with the electric vehicles and also having more ECUs and software for the autonomy, That's going to generate a lot of heat, and that heat will require managing. And so there's quite a lot of effort going into coming up with more efficient ways of removing that heat from the components, and perhaps being able to use it more productively elsewhere in the car, maybe for heating in the interior, for example. So as a result, there's people developing novel kinds of thermal interface materials, some of which are based on graphene or carbon nanotubes, to take the heat away from the electronics, so that you can thus operate them more effectively. They'll work better when they're a bit colder. So this is another big opportunity as you move towards EVs. It's not necessarily quite within the realm of electronics, but there's certainly a lot of interest from the chemical manufacturers in improving these kind of materials. So moving on to the interior, I think this is where the biggest opportunities are. And so I've split this up into kind of 4 different sections. So one is HMI technology. So HMI standing for human machine interface. So basically anything that you can touch or that senses your presence or that you can interact with. Heaters for the interiors, not new manufacturing methods, and then displays and lighting. So I'll just start by looking at a few of the different types of printed and flexible sensors. And there are quite a lot, and so I've just given an example here. So you can have pressure sensors, which can be spread over a matrix, and so you could have a sort of flexible film like the one shown here that you could put into a seat, for example, that can detect the pressure as a function of X and Y. You can do sort of similar monitoring spatially of temperature, as I've just discussed for the batteries. You can have light sensors, so organic photodetectors or photodiodes. You can have gas sensors for monitoring interior air quality. Capacitive strain sensors are maybe a little bit less relevant in the car, but you could monitor how much the seat is stretching, for example. And then printed electrodes, in which you might want to use for monitoring passenger well-being. So there's some discussion about how you can kind of track the alertness and the health of your driver, because if they crash, then obviously that's bad for everybody. And so could we be incorporating electrodes into the steering wheel, for example, or pressure sensors into the seat to monitor the heart rate while you're still wearing your jumper? There's a lot of opportunities for sensors within the interior in terms of how it engages with the driver and passengers. So to give you some examples here, I've just highlighted these integrated capacitive switches that I kind of mentioned briefly earlier. And so here on the left, there's some from the Volkswagen ID.3. So rather than having 4 buttons for your rear windows, instead you've got some capacitive sensors, and then the actual metal on those capacitive sensors can be printed, and we'll come on to that when we talk about in-mould and film insert moulding. And so capacitive sensors, from the point of view of the manufacturer, bring quite a lot of benefits. They're cheaper, there's fewer parts, there's less to go wrong. They can also sense proximity as well as contact, so they might light up before you touch them, for example. In these health-conscious times, you can wipe them clean because there's no grooves around the buttons. And there's a rather nice example over here from the Ford's latest EV, where they've actually put a kind of dial onto a conventional touchscreen, and then there's some little conductive materials inside that dial, and then as you rotate it, it interacts with the touchscreen much as if you were circling your finger. So that's the kind of best of both worlds type approach, where the driver or passenger gets something tangible to turn, but fundamentally there's not really a lot of mechanical parts going on there. It's just a touch screen that this has been attached to, and then clearly you can change the functionality depending on how you set up the touchscreen. So this is, I think we're going to see more and more of these integrated capacitive switches everywhere. Whether the passengers like or the driver likes them is perhaps beside the point. You're not necessarily going to get them on a Bentley, but it does make it cheaper for the manufacturer, and people will probably get used to them, and you save all of those assembly costs of having to install all of the buttons. There's also I'd like to be a move towards some integrated pressure sensors. And so if you think about pressure sensors at the moment, you sort of tend to think of just a single point. So capacitive sensors in general can't detect pressure. They'll just detect the presence of a conductive object, your finger, for example. But if we take pressure sensors, there's quite a lot of innovation here, making them on using flexible printed electronics, even making them stretchable. And there's some examples where they can be incorporated underneath some leather. So, if you touch this leather in different places or stroke it in different directions, or even press it with different pressures, it will be able to detect those gestures, but still look, have quite a luxurious feel with this kind of leather surface. And so this enables you to have a sort of three-dimensional touch. So this little graph shows you the pressure being applied as a function of X and Y. And that would enable you to have sort of more complex gestures. So rather than simply, swiping or pinching to zoom, you could control how quickly that pinch to zoom happens by how hard you press something. Or, you could change the volume on the stereo by how hard you press. And that's kind of functionality that at present isn't really there, and will provide another way of differentiating the interiors. I'd like to move on to the displays. And so I think it's kind of a fairly uncontroversial statement to say that over time, we're going to get more and more displays appearing in our automotive interiors. The most I could find was this example from Honda, where I think they've got 6 displays just in the front, never mind any displays in the back for your children. And so these include replacing the wing mirrors with cameras, so that's got benefits in terms of air resistance, having displays for the passenger so they can watch TV or something while you're driving, and having a display that replaces the rear view mirror. And I think over time, you're going to get more and more displays in the car. They're actually sort of relatively simple for the manufacturer to install because, they can just buy those from a third-party supplier, and the display industry is obviously well established. But they do provide a kind of, not at least at present, a really nice way of differentiating your interior. Certainly, I haven't seen many car interiors that look like this one from Honda. And this is, of course, in an electric vehicle because the manufacturers like to put in lots of modern technology to try and fit with the idea of sort of moving into the future with an EV. And at present, most of these displays are LCDs because, quite simply, they're cheaper. But I think some of the manufacturers are interested, particularly in their more premium models, in transitioning towards OLEDs. Because customers are used to OLED screens, from their phones. They kind of expect that kind of depth of color and contrast ratio. And so I think that transition is one that we're going to see. I think also we'll see displays in more and more places. So, it's fairly obvious looking at this picture that you have these pillars that, obscure some of your view of the road. And if you could replace those or cover those up with kind of a conformal display that would then just look like the outside with some cameras, of course, you'd eliminate any blind spots on any tricky junctions. And I think that would be, and also, provide a nice feeling of spaciousness. And I think that would be quite desirable and something that's completely possible with flexible displays. And just mentioning flexible displays, this technology is already here. You may have seen some of these flexible phones, and there's more every year. You go to CES or something, you'll see more and more of these flexible displays. And at the moment, they're very expensive, but it will be easier to make them that in terms of durability, that you don't flex repeatedly, but instead just curve once around the pillar, for example, or just curve slightly within the interior so the driver gets a better view. You won't have to worry about, will it withstand 10,000 folds? So I think this is something that we're going to see. Again, it's all about differentiation for the manufacturers. They can buy a kind of, relatively speaking, off-the-shelf technology, install it in their car, and then charge a lot more for it, and add some premium features. So I think that is certainly a technology that we'll see in cars, even if we haven't quite seen it yet. Another interesting technology that's particularly relevant to electric vehicles is integrated and transparent heaters. So if you want to heat your car at the moment, you basically use the air conditioning system to blow some hot air around. And particularly if you've got a large car, this isn't particularly efficient. You end up with that air being blown around everywhere. Some of that heat's ending up in the boot or in the back seats where nobody is. And ultimately, that kind of what uses up a lot of energy from the battery and reduces your range. So this German firm has come up with this rather nice idea of integrating transparent heaters in the interior. So they could apply these over existing surfaces with like a very thin film that will get hot. So you only need to heat up the touch points. So, anything that you might touch within the car. So not just the seat, but, any of the armrests or the center console or the top of the dashboard or any surfaces within the car. And this, according to them, could lead to reducing the heating power by 20%. So that's a sort of non-trivial gain in battery life or range. And even if you just go to printed heaters that are just below or just under one layer of fabric rather than embedded deep within the seat, you'll reduce the thermal mass, and so that means it will take less time to heat up, which is obviously desirable for the passenger. You can say, I want my heated seats on before I get in. It will take it 3 seconds rather than 5 minutes to warm up. And so I think you'll still get air being blown around the car for the cooling. But I think you'll also end up with more of the surfaces, like the armrests within the car being heated. We've already seen heated steering wheels. They're pretty well established. But I think that trend will kind of extend a little bit and start heating up surfaces that the passengers might touch, for example. The next sector I'd like to talk about here is in-mould electronics. And so the basic idea of in-mould electronics is given with this little flowchart at the bottom. And it's an alternative to combining all of these buttons. And so the idea here is that you print your conductive films and then conductive ink traces and dielectrics over the top. And you could even pick and place surface mount devices if you want. Then you do some thermoforming, tidy it up, and injection mold into the back. And then that enables you to create a curved array of capacitive touch sensors. And you can even integrate lighting into there as well. And so you can see this at this example over here at the top. This leads to significant improvements in size, complexity, assembly costs, weight. So it's quite a big benefit for the manufacturer. Here's the inside of an overhead console made in the conventional way with all of these switches. Here's one made with in-mould electronics where we've printed, or someone's printed, these conductive traces. And it's fairly obvious at a glance that this is much simpler, much lighter, and probably much cheaper to make. So if we have a look at a few examples, these are just some prototypes. You can see that you can actually have some quite significant curves in there. As I say, you can put lighting around, and we see a lot of interest in in-mould electronics. The car manufacturers have got to kind of spend more money than previously on the batteries and the powertrain, because that's obviously a newer technology, so it's still getting cheaper over time, which is not really the case with the engines. So they need to try and save money elsewhere if they want to improve the battery performance and still have an acceptable price for the customer. And so one of these ways is to make a relatively futuristic looking interior that's much cheaper to make and is lighter by transitioning towards in-mould electronics. There's a very similar approach to this where you do the steps in a slightly different order. Basically, you do your thermoforming first, and that's called film insert molding, and it offers similar benefits. It's perhaps slightly more process intensive, but this has already been commercialized, and I believe it's being used for some steering wheel controls. And you have pretty much the same benefits. You get rid of the buttons, and you can replace them with integrated capacitive touch switches. So there is another manufacturing method that would be associated with printed and flexible electronics that I think maybe doesn't get enough attention as it deserves to, and that's trying to replace wiring. So in a conventional car, you have a sort of wiring harness that's made by an external supplier. And then they'll have mapped it all out on a board and done all the cable ties, and then hand the manufacturer this sort of fairly heavy set of wiring, and that's done basically still a manual process, and thus is prone to some errors. It's also quite heavy because you've got to have all of that insulation for all of the wiring. And so the suggestion is that you can replace that by printing the wires onto injection molded parts. So obviously, if you used 3D printing to make the plastic parts, from the ground up, then that would be a very slow process. So for these larger items, you can take an additional bit, some manufacturing that's been made by injection molding, some plastic, print your wiring onto it, print some dielectric material over the top, and then your wiring becomes integrated into the actual material itself rather than just a separate wiring harness. And so this would make everything lighter, potentially be cheaper, and be less prone to mistakes, because apparently most recalls come from wiring issues. And if you're doing that digitally, then that won't be an issue. And you can even use this kind of approach to spool out thicker wires. So you can't really use printed electronics for wires that require high current capacities, but with this approach you can spool out some of the wires and then embed them within the film, within the plastic surface, using fused deposition modeling, again reducing the amount of insulation that you needed. Or to look at it another way, the insulation is part of the structure. So I think this is quite a promising approach. I think it's a few years, 3 or 4 years maybe, from appearing in any vehicles, but it's quite a promising technology. The other manufacturing approach that I'd just like to mention is this idea of hybrid electronics, where you try and take the best of both conventional electronics and fully printed electronics. And so this is kind of this sort of best of both type approach, and you take all the benefits of one of them, the conformable, printable, lightweight aspect of conventional printed and flexible circuits, with the processing capability of mounted integrated circuits, and you combine them. And then this enables you to basically reduce the weight and improve the conformality of your circuit boards anywhere in the vehicle. So you no longer do you have to worry about, I've got to fit this rigid circuit board in somewhere, and that's kind of relatively heavy because all this weight adds up. Instead, you can have something that's flexible, lightweight, but still capable of some significant processing, because you've mounted a packaged IC or even a flexible IC in some cases onto the circuits. So if we look at a prototypical flexible hybrid electronic circuit, it can be quite difficult to define, but we see something like this. And so you'd have some kind of flexible circuit where the antenna maybe, and probably not so much within a car, but there are lots of antennas being used in cars, to provide mobile phone signal or communicate with toll booths or whatever. All of these aspects could be printed. You could maybe even print a display on there as well. But you'd be mounting the processor and the memory. And so this is just a sort of schematic. You could apply these circuits to any application, sort of smart packaging, healthcare, wearable skin patches, or anything like that. But it's a kind of emerging manufacturing approach that's kind of halfway between conventional electronics and printed electronics. And if we just look at how to define it, I've basically defined flexible hybrid electronics as containing these kind of core features. So a non-printed, mounted, produced via photolithography integrated circuit. It's got to have something printed, and it's got to be flexible, but doesn't have to contain a range of these other features. So I'll just try my last slide on this section before I move on to the exterior. I'd like to sort of summarize all of the different technologies that I've discussed with reference to the interior, and I've plotted them on this kind of two-dimensional chart where I've looked at the manufacturing cost and plotted that above the functionality, or sort of the amount of differentiation. How novel is this capability? Does it actually offer improved performance to the customer? And so we can see that actually we get a whole range of different things there, and that shows the kind of scope of the sort of business models that printed and flexible electronics can slot into. And so we sort of unsurprisingly get a kind of diagonal line roughly across here, in that you're willing as a manufacturer to spend more on technologies that are going to add value to the customer, and that you can obviously charge more. So an OLED display here would be the kind of classic example. If you covered up my A-pillars with a flexible display, it would reduce the blind spot, make the car seem more spacious. I'd probably be happy to pay more for that. Whereas things like printing the electronics onto a 3D surface, the customer probably doesn't care at all. They probably won't even know it's happening. And so the functionality hasn't really changed. And so the only motivation to introduce that as a manufacturer is if it's going to make things either cheaper or more reliable, and hence require less maintenance in the future. So there's a whole range of things kind of along this spectrum. And I think, when you're talking about printed electronics, there can be a lot of focus on reducing cost and we can do large area manufacturing, we can do roll-to-roll manufacturing, it's all additive, we use less material, thus it's cheaper. And that can kind of miss the fact that actually you can use these technologies to add functionality that is improved and that people are willing to pay more for. And to date, the best example of the most successful commercialization of printed and flexible electronics is undoubtedly OLED displays. And that's not because they're cheaper, it's because they offer a better experience. And that's arguably why they've been so successful. So that pretty much concludes my discussion on the opportunities for printed and flexible electronics in the interior. Moving on to the exterior, which is my last section. One of the opportunities here for printed electronics is with the sensors as we move towards autonomy and maybe not full autonomy, but advanced driver assistance systems or ADAS. It's important that the car can sense as much as possible, and because it's not being that vision isn't being used by a human, we don't have to constrain ourselves to the visible spectrum. And so there's quite a lot of potential, I think, for shortwave infrared imaging. And so here are some examples of why that might be beneficial. And so if you look at this person here who's crossing the road, in the fog, it's almost impossible to spot them. But if you use a shortwave infrared camera, then it's much easier. And that's the case because at longer wavelength, light scatters a lot less. As you go to longer wavelengths, you're going to get fewer reflections off the water molecules or dust particles. And thus, it's much easier to obtain a high quality image that you could then either convert into a regular image to help the driver, or more likely process using sort of machine learning, some kind of image processing algorithm to inform your autonomous driving system. And so what's this got to do with printed electronics, you might ask? Well, it comes in the form of these hybrid sensors. So as you might know, silicon sensors can't measure any light, or they can't detect any light above about 1,000 nanometers, and even above 900, they're not very good. And so if you can extend the wavelength sensitivity of a material of your silicon by printing a layer of either an organic semiconductor or quantum dots on top, kind of something like this, then you can use the kind of back end, the readout integrated circuit that's silicon, but it detects up to say 1,500 or 2,000 nanometers. And so whilst not flexible, this top layer is sort of processed from solution. So you can do that with quantum dots or organic semiconductors, as I say. So it is already possible to image in the shortwave infrared range, so between 1,000 and 2,000 nanometers, but it's very, very expensive. That's kind of reserved for scientific instruments because one of those sensors might cost you $10,000 or $20,000, which is obviously completely absurd for a car. And so being able to make them on a sort of silicon backplane just by printing a layer over the top, you could reduce these down to the hundreds or even tens of dollars, and then it becomes a much more compelling proposition, to supplement the other sensors that we hear so much about, such as LiDAR. I think that this idea of sort of sensor fusion, of using multiple different sensor methodologies so that you have some redundancy, is something that you hear more and more about, and I think that shortwave infrared imaging is likely to be part of that. So another kind of completely different application here is these transparent conductors. So everyone will be familiar with transparent conductor, or the little heating strips you get on the rear window for defrosting them. But generally speaking, you don't get that on any of the other windows in the car. Sometimes you get very fine metal lines, but customers apparently don't like them because once you've seen them, they kind of keep annoying you and you keep spotting these little lines. So there's quite a lot of interest in developing transparent conductors, both for the lights and the glass, as you might imagine, but also, and perhaps more importantly, for the sensor housing. So if you're going to have lots of cameras around your car, and every year there are more cameras applied to the car, then ensuring that they're not obscured with frost or mist is very important. And so having a transparent heater that could be made from either metal mesh, carbon nanowires, carbon nanotubes, silver nanowires, graphene, various technologies that can be heated but yet remain transparent, I think it is a really important application. And it's also potentially quite a big market if you could put this on the on the front windscreen, there's quite a lot of glass there. It's at least a square meter, and it would be really helpful in winter to not have to worry about the frost. And you could just do some demisting just like you do on the rear window at present. And so sort of simpler versions of this have already been adopted. And so this is again done mainly via In-Mould Electronics, in which a thermoformed piece of plastic has some wiring kind of embedded in it. And then clearly you can heat up that wiring to get these frost or mist off your lights. And it's important to recognize that this is more important for electric vehicles because, unlike an internal combustion engine vehicle, electric motors and the sort of power systems aren't pumping out anywhere near as much kind of waste heat. So your car, it's not a case of just turning your car on to run in the morning for 5 minutes before you get in and everything will warm up and defrost, because it's not going to be generating that much heat, and any energy, you don't want it to be wasted if that's going to reduce your range. And so being able to target the heating just at the lights, in this case, I think is quite compelling. So another technology for printed electronics in cars is, of course, these OLED and ultimately mini LED taillights. So you see a lot of interest from Audi. Particularly, they've been very successful in commercializing OLED lighting in their rear lights, mainly as a point of differentiation. You could just use LEDs, but they're not quite as premium. And so if you want to create something that's distinctive and quirky, then OLED lighting is the way to go. And again, this is all, as you can see from these photos, this is already employed in commercially available models. And Mercedes are doing something similar, and BMW once did a while ago, but I don't think they're continuing with it. So that's certainly an opportunity there. And again, it's a great example of printed flexible electronics being used to kind of add value to the customer rather than make something cheaper. If you're maybe in a slightly less premium vehicle and you can't quite stretch to these OLED lights, but you still want something distinctive, then you can have LEDs mounted onto a flexible substrate. And so this is being developed by Rahini, which is the company that's kind of come up with this method of cheaply mounting many micro LEDs onto a flexible substrate, and the automotive supplier Magna. And again, you'll be able to get something that's flexible, conformal. You can have different patterns. You can address each of these LEDs individually. So if you want to send a message to another driver, if they've annoyed you, you can presumably tell these LEDs to spell out some words or something. And perhaps more usefully, you can have it on the front of the car for communicating with pedestrians. And that brings me nicely on to the next slide, which is this in-person communication with pedestrians in autonomous vehicles, where at present, if you want to cross a road, you tend to look at the driver, you catch their eye, you kind of see that they've spotted you, and thus you step in front of them. But clearly for an autonomous car, it's not really possible because the driver won't be looking at you. And so you're going to need to put some kind of simple, relatively cheap display onto the front. It doesn't need to be high resolution. It doesn't need to be particularly high quality. And it needs to be flexible, probably conformal with the bonnet, and ideally deformable in the case of an accident. And so printed flexible electronics for this are quite promising. And again, something like those micro LEDs that I showed you are going to be much cheaper than OLEDs, and are probably quite well suited to this kind of application, because the resolution doesn't matter too much because you're going to be quite away from the car. So moving along, I think this is one of the last technologies. So come towards the end of the talk. I'd like to mention putting organic electronics onto onto vehicles. And here's some examples of organic photovoltaics. And so they haven't necessarily been a particularly big commercial success so far. But we are seeing some more interest in using them for indoor energy harvesting. And you can sort of win in the automotive sense because of the lightweight and the conformality. So curved, both for style and for aerodynamics. And so putting large squares of silicon on there is perhaps not desirable. So having some kind of thin film photovoltaics that can both save weight and wrap around the car to harvest a bit of extra energy to top up the batteries. You're not really going to be able to power your electric car entirely just from the sun, but if you parked it in the sun, you might get another 10-20 kilometers of range. And you might also, as the technology develops, get some semi-transparent PV, which you could use on the rear windows or the side windows, for example, which would be able to harvest mainly light outside the visible spectrum, still enable the passengers to see outside, but again, harvest a bit more energy. And you might imagine this kind of technology in trucks, for example. So on the roof of a lorry or down the side of a curtain-sided truck, you could put some PV panels, obtain a little bit of extra energy. Obviously, the truck's a lot bigger, so you can harvest more energy because of the area, but you need a lot more energy to drive it. So in terms of the range, it's probably not going to be a huge amount extra, but if this is cheap and widely available, every extra kilometre of range is a bonus, and you can put this onto your car. And you can also supply the air, power the air conditioning, and whatever else without using up the battery while the truck is parked. So if we look again at people trying to employ this in cars, so there are lots of examples here from manufacturers. Here's one from a concept from Ford. Hyundai have a concept. There's a startup in Germany called Sono Motors that's planning to launch a fairly small sort of city car with a lot of solar panels that they claim can have 30 kilometers of range, even in Munich, which is presumably cloudy. And so, I think there are, over time, I think we're going to see more and more photovoltaics being used in electric vehicles. At present, those are going to be silicon because that's the highest efficiency. But over time, these are likely to become either thin film, or they can also become tandem PV, in which you put a layer of perovskite, for example, over the silicon to increase the efficiency slightly. So that brings me sort of towards the end of my talk. So just a little recap, we've covered all of these sections. So what is printed flexible electronics? Why do we want to put it in cars? And then looked at these different application areas. So I'd like to finish with a couple of slides showing a roadmap. And so this is kind of where I've envisaged these different technologies being first integrated in a car. So the sort of start of the arrow is a kind of estimate or forecast of when you're likely to see a car that you can go and buy, not necessarily all of them, but a car that is available for purchase, not a concept, that's going to have these kind of technologies. So what you can see here, if you look over on the left, we can already go and buy a car today with these integrated capacitive switches. There are also some printed heaters in the seats, and film insert molding is being used to make those capacitive switches. But over time, we think you're going to get pressure sensors, transparent printed heaters within the interior, maybe on top of things. You're going to get some in-mould electronics, to reduce the manufacturing costs, and there's printing onto 3D surfaces that I mentioned. If we look at the exterior applications, and I've also included the batteries in here, I think this printed battery and heating monitoring will arrive sort of fairly soon. These transparent heaters on lights via in-mould electronics are already available. Via transparent conductors is probably more challenging and much more costly, so that will take a bit longer. And we'll also see something I haven't really spoken much about, which is the incorporation of antennas via printing. So cars are going to need more and more antennas, and so you're going to get those printed, we believe, onto plastic panels in the car, and perhaps also onto the windows as well, because clearly the metal bodywork isn't really, it can't be used for printing antennas onto. So that brings me to the end of my presentation. I'd like to mention that all of this content that I've spoken about today is featured in this IDTechEx research report. So, ultimately, we're a company that produces this kind of content and sells market research reports. And so there's a lot more detail on the topics that I've mentioned. I think it's about 350 pages. So we've got market forecasts of all the different categories that we've looked at, looking at market sizes as well as just the timelines. There's lots of company profiles that we've interviewed. And if you'd be interested in finding out more about that, or indeed any of our other content, then please email the Business Development Director, Teresa Henry. This kind of commercial potential and different applications. We have a very long list of those kind of technologies here. Just highlight a couple. There's flexible hybrid, in-mould electronics. I've mentioned both of those today. And of course, quite a lot of applications in things like healthcare and wearable technology as well. So thank you very much for your attention. I'll answer any questions.
Thank you, sir, for your information and for very informative talk. Let me check is there any question? No, sir, there is no question. I think it is somewhat very much elaborated talk, so no confusion at all. Everything is clear to everybody. So, sir, please accept our sincere gratitude. And on behalf of the convener, Dr. Tarun Dubey, he is extending his gratitude for all your cooperation. Please accept his sincere gratitude, and thank you very much for your. Please, you have accepted our invitation. Thank you very much, sir.
No problem. All right, thank you, and apologies again for the technical issues. Thank you.
Problem,
all right, bye.
Thank you. So now we are meeting around 2:15 for the next paper presentation, parallel session for the participants. Till then, we are moving, signing off. Thank you.